I had a question from a student um, in relation to one of the quiz questions. I believe it was on quiz 1. Pretty sure it was on quiz 1. Might have been on quiz 2. Actually, I take it back. It was on quiz 2. But it was with regards to a percentile, and it was on the wording. And I realized in class I wasn't super careful or good about making a distinction between the wording that I would use, because a lot of times I would say like, oh, something is equal to or worse than, and other times I would say something is equal to or better than. And it's in the context of how the question is worded. So if you remember, this is like our distribution with our mean in the center, right? And a given frequency, whether it's simple or grouped, there is some raw score that we want to find the percentile for, right? So let's say our raw score is here, and that's going to be represented by X, okay? So what happens is when we calculate the percentile, we basically say from this point over, right, being worse than scores and better than scores, or best and worst, right? From this score, we say the percentile represents the area to the left of that point. Okay, so this is the area that the percentile would fill. Okay, so with regards to the question I got, was how do you word what the percentile means in the context of a given question? And so if I were to say like someone's at, that's the word I want to focus on. Someone's at the 60th percentile, that means they scored at this given raw score or better than all of the people on the worst end of the spectrum, right? If I said someone scored within being the key word here, right? Someone scored within the 60th percentile. We don't know exactly where they scored in there, which is when I use the wording they scored at or worse than a given raw score, right? Because they're within this area, we just haven't specified where they are. But if someone is at a certain percentile, they've scored at or better than, because we've identified their location in the distribution. So I just wanted to make that clarification before we get started, because I thought it was a very good question to clarify. So I'm going to share, let me close, I have a bunch of stuff open now. But I'm going to share my screen and we'll get rolling with the PowerPoint. Let's see the portion. Get rid of that. And I'm still doing dad jokes and memes because even the people taking a vacation can appreciate them. So this week I had a theme of body image. So I found this while I was perusing Instagram at midnight, and it's of deformed people. I don't know why. They just looked really funny. That guy looks like he's constipated when he's walking. Anyways, yeah, that was pretty great. My next share is trying to fit into skinny jeans. This really summarizes the effects of coronavirus quarantine time. I feel very relatable. And then my last one is about potatoes. Anyways, that's more of a dad joke, but hopefully people get some enjoyment out of that. So today our topic is mainly pulling from chapter 5 and 6 out of the textbook. And we're gonna first talk about measures of variability. So last time we talked about measures of central tendency, right? And that was primarily looking at where the center or the central trends, right, of our data are. And so we calculated the central tendency with mean, median, and mode. And so this week, we're going to be talking about variability, which is more relative to the spread of the data. Okay. Lastly, we're going to talk about the normal curve. Okay, and the normal curve kind of ties in our conversation with regards to measures of central tendency and measures of variability. And we'll talk about there's certain characteristics that make up the normal curve, and then we'll talk about different factors that are going to play into changing the shape of what we would consider normal. And then there's this cat. I just like cats. All right, so starting off with measures of variability. Again, variability is generally going to describe how spread out the data is. So some of these might be familiar to you. Most everyone has heard of range before. That's more of a introductory algebraic type of equation, right? Last week, a little bit, we talked about the interquartile range. We'll talk about it a little bit more this week. And then we've already worked with standard deviation, but we'll go into how standard deviation and variance are similar to each other, how they are different with respects to their formulas, but generally how they're affected by different parts of your study are pretty similar. And then the last measure of variability we'll talk about is the coefficient of variation. So we'll go through each of these one by one. The first one starting with range because it's the easiest, okay? Well, this is basically just the difference between your highest and lowest scores in your data set. We would use a range if we need a quick and easy calculation, right? It's a very, very general estimation of the spread of your data. The problem with using this in more critical situations, I guess would be a good way to say it, is that it can change very dramatically if there are extreme scores introduced to the data, because you're taking the minimum and the maximum. Usually outliers or extreme scores are going to be at the outside of your data set. So let's say we were looking at the pull-ups example from the last activity, right, where we ranged from 3 to 20, right? Let's say some kid in the class that we measured had or was able to perform 30 pull-ups, right? That's relatively far away from the closest maximum that lays within the distribution. So introducing extreme scores can drastically change the range depending on how extreme those scores actually are. Our next measure of variability, again, we saw this last week, right? And that's our interquartile range. So we can split up our distribution basically from the 0th percentile to the 100th percentile, and we split it up into quarters, right? So think like quarters like money, okay? So basically these quarters or quartiles, right, represent certain percentile markings in the distribution. We're most interested in the 25th percentile, which is at Q1 or quartile 1, and the 75th percentile, which is at quartile 3 or Q3. And the reason we're more interested in this part, which will make a little bit more sense when we get back to or when we get to the normal curve a little bit later, is that this information, if you take 75, where's my cursor? You take 75 minus 25, you get 50%, right? So by taking the interquartile range, right, or looking at what raw scores exist at the 3rd percentile or the 3rd quartile versus the 1st quartile, is going to give us information about how spread out the majority of our data is, because that middle 50% should hold most of the raw scores that are in the data we're investigating. So we'll actually come back and use the interquartile range. It's very helpful in identifying outliers, or at least it's a commonly used method in identifying outliers in a given data set. But as far as terminal statistics go, we don't typically use the interquartile range past just calculating it or using it to calculate for outliers. So it doesn't go into any major statistical tests like t-tests or ANOVAs. So again, it's a good indicator of spread because it tells us information about the middle 50%, not influenced by extreme scores, which is why we use it to identify extreme scores. And I think that'll come like quite later, right? And we often use it with ordinal data, so data that is ranked or data that is highly skewed, okay? And again, use it with highly skewed data just because it doesn't include the extreme scores in its calculation, because those would be closer to the 0th quartile or the 4th quartile. Another common measure of variability is variance. So technical definition of this is the average of the squared deviations from the mean, right? Deviation in statistics just means the distance that a certain data point is from the mean of the group that it belongs to. So in a formula, this is what it looks like. You guys don't need to memorize this for this class, but I think it's good to understand the different components that go into measuring variance. So this top part up here, this is a Greek symbol sigma, represents the summation of this given function. So basically what we're doing is we're saying every raw score, or for each raw score, we're going to take the difference between that raw score and the mean of our group, square that value, add up all of these squared values, and then divide it by the total number of people who are in our sample or population, right? That top part is referred to as the sum of squares, right? And you'll know from basic algebra, right? Anytime you square a number, whether it's positive or negative, the result that you get of that squared number is positive, right? So this sum of squares eliminates negative values. Okay, so it kind of just gives us the general direction, or not direction, but the general deviation from the mean out of the entire data set. Okay, so if we use this in a mathematical example, let's say we were given these raw scores, right? This is a very small sample, but we were given those raw scores and we have a mean of 21 and a total number of 8 in our sample, 8 values in our sample, okay? The way that we go about calculating the variance, right, is we say, what's the difference between our first x value of 12 minus the mean, which is 21, right? That difference would be 9. Okay, so that's kind of like the first step we could do all the way down. And you can see these variations are both in a negative direction from the mean as well as a positive direction from the mean. So the purpose of this sum of squares, right, is that we square each of these distances, or the differences, right, and we end up getting positive values. We end up adding these positive values, or these squared values, and that ends up giving us the numerator, right, or the sum of squares in our variance calculation. From there, if we just divide by the total number of observations we have, we get the variance. And this is going to be in whatever units our measurement is, right? So if we were, let's say these were vertical jumps in inches, right? I'm trying to think of examples that actually make sense with these numbers, but we're measuring people with a vertical jump in inches. Our variance for our sample would be 36.5 inches. So the variability, or the variance, is going to adopt the unit of the measurement that you're taking. A spin-off of variance is what's known as standard deviation, and this is probably the most common measure of variability that we use in statistics because, similar to the mean, it's used for a lot of different statistical calculations. And it's pretty much just the square root of the variance, right? Again, deviation is, it's referring to how far a given data point is from the mean. So we're still taking that difference, right, of raw score minus the mean, squaring it, taking the sum of squares, dividing it by total number of observations. Standard deviation just takes the square root of that variance, okay? And basically what we do with this information, right? So this, using the example from the previous slide, we can see standard deviation is 6.04. From this, we can create a bell curve, right? By saying, I know my mean, and then if I add, I think in that last example, the mean was 21, right? We can make a bell curve and say, all right, one standard deviation away from the mean, right, is 6.04. Let's keep the inches concept, right? So 21 plus 6.04 inches gives me my value, or the raw score that would land at the first standard deviation, right, in the +1 standard deviation direction. From that value we calculate at the first standard deviation, we can add an additional 6.04 to get this, what the raw score would be at +2 standard deviations, and then we can add 6.04 again to get the raw score at +3 standard deviations, right? We can do the same thing in the other direction. So that's usually why when you see in research, right, someone gives you the report of the mean plus or minus the standard deviation. That's why, right? Because standard deviation just represents kind of the incremental deviation away from the mean that we get in a more standardized version, right, in representation of +1, +2, or +3 standard deviations. So I'm planning on drawing a picture of this in a little bit so that it should make more sense. But that's kind of the general concept of how we work with standard deviation. Now, there's one thing to keep in mind when you're looking at measures of variability, specifically variance and standard deviation, and that is who you're measuring, right? Because we know that samples are pulled from populations, which inherently means that samples are always going to be smaller than populations. Our goal as researchers is to make sure that our sample is representative of the population, and that we'll talk about this in a later lecture, but that the power of that sample is good enough such that the results we get from that sample could be inferred on the actual population that sample was drawn from. So what we need to do in our statistical calculations is add in this correction factor called the degrees of freedom. And this is one thing that I hate because you guys have heard degrees of freedom in several different contexts probably by this point. Everyone in this class should have taken biomechanics, and you'll remember degrees of freedom represented how many ways or directions you can move at a given joint, right? We've also heard degrees of freedom in the context of the degrees of freedom problem in motor control, and that's how do we coordinate all of the given degrees of freedom at a particular joint. Statistics is completely different, okay? So kind of throw out all of the degrees of freedom definitions that you have previously encountered, okay? Degrees of freedom in the context of statistics is just saying the numbers of values in a data set that are free to vary, okay? And in the setting of variance and standard deviation, degrees of freedom is n-1. Okay, it won't always be n-1. There are situations where we have multiple samples that we're working with that plays into what the degrees of freedom are. There are some times where if we have different treatment groups and the number of samples. Both of those factors are considered. So degrees of freedom will pop up a lot, and it's a major factor in how we read a lot of the tables that we'll be using in this class. But just know for standard deviation and variance, the degrees of freedom we use is n minus 1. Again, n represents the total sample size. And the 1 is just correcting our problem, right? So why do we need the correction factor? Again, it's if we don't use it, we are assuming, right, that the sample is equal to the size of the population. We know this statement is not true, right? Because samples are subsets of a population, meaning they're always going to be smaller. So if we add in this correction factor, we kind of add in, or we're accounting for any error that might be made as a result of the sample being smaller than the population. So we can look at, these are sample variance and sample standard deviation equations, and you can see this degrees of freedom has been changed in the denominator, right? But if we take our original sample calculations, right, with the mean of 21 and the sample of 8, right, these two values, what were shown on previous, or were shown on the previous slides, and if we apply this degrees of freedom, you see that the sample variance and the sample standard deviation change. So we're basically, by saying we're not actually sure if our sample is, we know it's not as big as the population, but we're kind of adding in some degree or allowing for a certain amount of error, right, by increasing the variability that we calculate. Does that make sense? You guys can use like the yes or no functions.
So basically we are preparing ourselves for a worst case scenario in that sense.
Yeah. Yeah. Because it's very, very rare, unless your population is really, really specific, it's very rare that you'll get to measure your entire population, right? So we're accounting for this degrees of freedom kind of accounts for the people that don't get collected in your representative sample. Yeah.
Okay.
Mm-hmm. All right, so then our last measure of variability is going to be the coefficient of variation. This is a standard score. If you guys remember, standard scores allow us, or it provides us a method in some way to compare different samples to each other or different units of measurement to each other. I feel like we have a pretty good example of coefficient of variation and using it in the activity this week. But again, it's a standard score. I want to highlight that because some people always forget this one. And the standard scores we've already talked about are percentiles in this class. So this is another standard score you can add to your list. But basically, it's just taking the standard deviation divided by the mean, and you multiply it by 100. So it is represented as a percentage. Okay, so if we take this example here, right, where let's say we want to evaluate a person's level of fitness, right? We know fitness, at least in our major, like fitness encompasses a lot of different things, right? So are we evaluating someone's fitness based off of their endurance capacity, or are we basing it off of maybe, you know, resistance training and their muscular output? So we can essentially like compare two different groupings of measurements, or this could be one person and we can evaluate, you know, variability. Well, actually, no, let's not do, because you do need a group of people. You need a mean and a standard deviation. So X out what I just said. But we could take this group of people, let's say they were measured, or their VO2 max was measured, as well as their peak power output, right? And we could say their mean VO2 was 60 with a standard deviation of 6, and their mean peak power output was 1400 with a standard deviation of 200, using these units of measurement respectively, right? So for VO2 max, the way that we calculate our coefficient of variation would just be standard deviation, which is 6, divided by 60, the mean, right, times 100, and that gives us 10%. So we would say the sample that we've collected and measured VO2 max in has a general variability score of 10%. Okay. If we did the same thing for power output, it'd be 200 divided by 1400 times 100, right? And that would give us a coefficient of variation of 14.3%. So when you're evaluating or comparing two different coefficient of variation scores, usually we say that the lower percentage represents a lower amount of variability. A higher percentage would represent a higher amount of variability. So in this case, if we wanted to say or evaluate which of our testing variables has the most variability, it would be our power output. Okay, so again, coefficient of variation is a standard score, and it's a standard score where we can evaluate different measures of variability, basically. Okay. Any general questions on our measures of variability? Cool. All right. So that brings us to the normal curve. And then you're probably wondering, what does the rock have to do with a normal curve? Well, there's a bell in this GIF, so that's why I chose it, as a normal curve is often referred to as a bell curve. Ha ha ha, I'm so funny. All right, so a normal distribution is basically a symmetrical distribution of data, right? In a perfect world where the mean, the median, and the mode are all equal to each other, right? So this would be an example of a frequency distribution, which we've already looked at, right? And the frequencies of these scores, right, deviate from the mean in a very predictable pattern. So let's say our mean in this case is 50, and then we know plus or minus, right, at the next unit down, right, we have, let's maybe say the deviation decreases by 10, right? So from 50, the next score over has a frequency of 40, and the next score over has a frequency of 30, and the next score over has a frequency of 20, right? So this is very stepwise, symmetrical deviation as we get further and further away from the mean, and it's true on both the side above the mean as well as the side below the mean. And that's where we get this curve. If we smooth out, right, these points over this frequency distribution, it looks like a bell. And there's a specific rule that goes, ding ding, I don't know, I like cats. Anyways, there's a specific rule that goes with the normal curve, and it's called the empirical rule. It's also sometimes referred to as the 68, 95, 99.7 rule. And these numbers come from these relative percentages that should exist in a perfectly normal distribution. So S represents standard deviations, okay? 0 is in the center, so that's where the mean of our data set would lie, right? The mean has 0 standard deviations from itself, which is why it's represented as 0. But we can go +1, +2, or +3 standard deviations from the mean, and -1, -2, -3 standard deviations. We usually don't go past 3 when we're describing characteristics of a normal curve, just because you can see anything past 3 standard deviations should only represent 0.13% of a given population or a given sample. So it's anything past 3 is kind of insignificant to the majority of our distribution. But we get this 68, 95, 99.7 from characteristics of where our data are located. So between plus and minus 1 standard deviation from the mean, if we add these two percentages together, we relatively have 68%, right? Or 68% of our sample data or our population data should lie between whatever raw scores exist at minus 1 and plus 1 standard deviations from the mean. 95 comes in if we go from plus or minus 2 standard deviations. Okay, so 95% of the data should land in this area. And 95 should kind of sound familiar if you've heard of confidence intervals, right? And this is a very standard, I guess, boundary for assumptions that we make on the basis of normality. And we'll talk about that in a little bit. But 95% should land between plus and minus 2 standard deviations. And then if you guessed, right, 99.7% should land between plus or minus 3 standard deviations. And again, we can determine this by adding the areas, right, or the percentages within these areas under the curve. So if I wanted to know how many people are on the upper end of my distribution, right, or how many people are in the top 50%, or what's the percentage of scores that would lie between 0 and plus 3 standard deviations, I literally just add up, right, these 3 percentages, and I can get the answer I'm looking for. So the empirical rule, it's, again, based off of a perfectly normal curve. So we use the normal curve or a general bell curve design to represent the population. And we're always assuming that the population is normally distributed. And that is a very foundational concept, because when we collect our samples, if they have to be representative of our population, the samples too need to be normally distributed, right? So we kind of pull in this information if we wanted to find a percentile. If, let's say, we put a lot of studies together and we were able to figure out what a population mean and standard deviation are, we can use that information to help tell us where a person with a given raw score would be, or what percentile that person would be given their raw score in the distribution. And we do that by using z-scores, right? So again, standard deviations tell us how far away any given raw score is from the mean, right? Or just deviation from the mean. How far out are you going, right? So z-scores are kind of just a mirroring effect of that, right? And those are raw scores that are expressed in standard deviation units. So we say 1 z-score is equal to 1 standard deviation. And this, remember, standard deviations are still calculated in the units of the measurement that's taken. This is just in general, if we were applying this back to this picture, right? 1 standard deviation would be equal to 1 z-score, right? -2 standard deviations from the mean would be equal to -2 z-scores. So we're not specifically translating, like, if the standard deviation, let's say, was 10 inches, right? Whatever the mean is, let's say it's 50 for simplicity, right? Plus 1 standard deviations, we would add 10. That would be 60. So 60 inches would be the raw score, or the raw value that would lie at 1 standard deviation from the mean, or 1 z-score, right? If we continued on in that direction, right, again, our standard deviation is 10 inches or 10 units of our measurement. So if we started at 50, we get 60, now we have 70, right? And 70 is our raw score that would land at the second, or plus 2 standard deviations from the mean, okay? So that's what I mean by z-scores are equal to standard deviation units, right? And we calculate this, we can do it in a population or we can do it in a sample. Generally speaking, mu and x bar are the means, right? A mu is a mean for a population, x bar is a mean for a sample. And then baby sigma is the standard deviation for a population, where usually we just say SD for the standard deviation of a sample. But we're primarily going to be using this notation in the class, okay? But using a z-score can help us determine the percentile or the probability that a value lies within a certain range, right? So z-scores are another type of standard score because, again, we can use units of a given standard deviation and convert those units to say, well, this value represents 1 standard deviation from the mean or -2 standard deviations from the mean, and we can convert that notation into a z-score, right? Because the z-score is proportional to standard deviations. So when we look at this, we can use a table to help us figure out what percentile is associated with a given z-score. And you might have seen this before. Are you guys able to see the numbers okay on your screen? I have mine in presenter view, so they're like freakishly small. But I posted the Z table if you want to look at it online. It's in a PDF. But basically, we have 2 Z tables. One is positive for positive z-scores or values that are above the mean. So in this example, this is a positive z-score table, and you'll see that at the mean, we exist at 50%, right? All of these values are representative as a probability value, which is always going to be between 0 and 1. So if you multiply any of these numbers by 100, it becomes a percentile, okay? But you'll notice zero deviations or 0 z-scores from the mean, we're at 50%, which is where the mean should land in a perfectly normal distribution. If we go out to 3.49 standard deviations from the mean, or basically 3.5 standard deviations, you can see that we've almost reached 100% or the 100th percentile, okay? So conversely, the negative z-score table is going to give us the bottom 50% of our table, okay? And remember, percentiles are representative of the area to the left of a given raw score. Z-scores operate in the exact same way. So once you identify what your raw score is, right, we take that information, subtract it from the mean, divide by the standard deviation, you get your z-score, okay? The z-score is going to say at this given point in the distribution, let's say we were had a z-score of 1.12, right? So let's say middle of this distribution would be the mean. At a z-score of 1.12, our percentile is going to be, I believe that says 86.86%. I could be wrong. It's really small on my end. But that number, right, means that at this given raw score, that's at the 1.12 standard deviation or 1.12 z-score, is that person has performed at or better than, right, about 86% of a given sample or a given population. So with that, right, again, there's just more instructions on how to read, but the table. So when you're given your z-score, usually we do it to the second decimal place, right? And just like I read, someone with a z-score of 1.12, right? 1.1 is your starting point, and the 100th place kind of tells you what percentile specifically you're working at in the table. So again, at one big take home that I feel like a lot of people mess up on is that z-scores are going to represent the area to the left of the curve. To the left, okay? So in a case, I'm going to stop sharing for a second. In the case that we are use a bit of different lingo here. We'll do this, right? So this is, I'm just going to put M for the mean, right? If we wanted the percentile of a raw score, or if we want to know what percentage of people could perform or would be expected to perform worse than a certain value, right? Let's say our certain value is right here, okay? The percentage of people who would perform worse than this value would be the area to the left. So if we were looking at a z-score, right, for this given raw score, we would know the percentage that we're reporting is representative of this area, right? Let's say we wanted to look at this same raw score, right? But we want to say what percentage of people in a given population or a given sample would perform better than that raw score. In other words, we're looking for the area to the right in our desired answer, right? So this is what we want. But remember, if we're using z-scores to calculate percentiles, the z-score is going to give us the area to the left, right? So in this case, in order to get this red percentage over here, we have to say either 1 minus whatever this area is here, right? So 1 minus that area, and that would give us whatever this area is here. Okay, so you kind of have to use it to fill in your blanks a little bit. The same thing would go for if, let's say, again, we have mean here. Maybe we want to say what percentage of people, or what's the probability that someone would score between X or raw score number 1 and raw score number 2. So now we've got 2 points of interest, right? And this is arbitrary placement of my X values, right? But my desired area is this middle part, because I'm saying I want to know, right, probability for the area under the curve that would land between these two scores, right? So in this case, we would have to find z-scores for 2 x's, right? x1 and x2. The z-score at x1 is going to give us the area from that raw score down, right? Let me do a different color, right? Our z-score at x2 is going to give us a probability or area under the curve that includes all of this over here, right? So in this case, we want to take this green area, right? Whatever that is, we want to subtract it from whatever this area is over here, ching ching, right? And that should give us this red area, right? All of this portion in here. We take the big chunk minus this little baby chunk, and we're left with the red probability that we want, okay? So this concept that the z-score gives you a percentile or probability of the chance that raw scores are going to occur, right, to the left of that given raw score is a very, very, very important thing to remember. Okay. All right, we are almost there. So this is just an example, right? You guys can practice calculating z-scores, and then you can practice calculating the percentiles. So I'll post the filled out slide, but this is primarily for you guys to like practice working forwards and backwards based on certain bits of information. I'll probably do a small video on calculating these so it makes a bit more sense if it doesn't already. So the last thing we want to talk about is what happens when you don't have a perfect distribution. okay, or if we're looking at distribution shape, right, the shape of the curve. First of all, just a summary, I'm getting ahead of myself, sorry. We use z-scores to calculate percentiles, right, which is the example I just gave. We also use z-scores to calculate confidence intervals. So that's where I was saying if you have that 95% between two standard deviations, that would also be equivalent to 9% between two z-scores, okay, or plus or minus two z-scores. So we can use that to create confidence intervals, which we'll talk about in a few weeks. And then we can also use z-scores to help us calculate skewness and kurtosis. And skewness and kurtosis are what happen when our distribution isn't normal. So the first thing we're going to look at is skewness. This is primarily looking at the measure of symmetry of our distribution. So in a normal, like this red one here, we have this perfectly symmetrical distribution, right? When we have the presence of outliers or extreme scores, if you remember from last week, there was a small example at the very end of the PowerPoint where we showed different calculations of mean, median, and mode. And what that calculation showed was that we had a bit of skewed data because the mean ended up being greater than the mode and the median, right? And so this is what happens. Really, skewness and kurtosis are measurements of tail activity. Tails meaning the ends of the distribution, right? So if you have a positive skewness, that means you have a right tail, right, that extend to values greater than the mean. So I like to think about it in terms, or remembering positive versus negative skewness is in terms of where the standard deviations are, right? So positive standard deviations are usually to the right, negative standard deviations are to the left. Positive skewness, right, is indicative of tail activity. So the tail is going to be on the positive deviation side. Versus negative skewness, the tail is on the negative deviation side. And this gives us information about our measures of central tendency, right? Because in a perfect distribution, or a perfectly symmetrical distribution, the mean, median, and mode are all equal to each other. But when we have presence of outliers, right, the mode generally is where the peak is, and the median is where the center of the data is with respect to the quantity of values that you're working with, right? But the mean is the average of all numbers that are included within this distribution. So what happens to the mean is it gets dragged towards the tail. So in the case of positive skewness, right, where the mean usually would have been associated with this peak, right? And that's generally where we can associate the mode and the median. What happens is the mean ends up moving this direction. So it ends up being greater than, right? If we read this the other direction, the mean ends up being greater than the median and the mode. This is the opposite for when we have negative skewness, right? So again, the tail is on the left side, representing that there's some extreme score that exists out here. And mode and median are usually associated with the peak of the distribution. So the tail activity, or that outlier, is going to drag the mean this direction, which means the mean is going to be less than where the mode and the median would be. Okay, so skewness is really pointing to if we have existing outliers or not. And we'll talk more about when we are going to accept a sample distribution compared to when we wouldn't. There's certain criteria that we describe a little bit more in the activity this week. The other measure of curve shape is kurtosis. And this is not necessarily looking at if we have the presence of an extreme score like skewness does, but rather how many extreme scores we have. So again, kurtosis and skewness, oh, I forgot to change this to kurtosis, but kurtosis and skewness are measuring tail activity. So in positive kurtosis, usually we see if this is our normal distribution in the middle, positive kurtosis is going to have a super, super tall peak and heavy tail. So if you think this tail extends all the way out here, and it might not be necessarily flush with the x-axis, but that means if there's a tall peak in the center and a long tail on the outside, that there's a presence of a lot of outliers, right? And it might be, you know, there's only one outlier at any given data point above or below the mean, but the idea is that you have too many for a given distribution. The opposite is true for negative kurtosis, right? So negative kurtosis, we have a flattened peak. I like to think of this in terms of moods. So a positive kurtosis, you're going to have a high peak because you're super happy. Negative kurtosis, you have a low peak because it's sad, right? But what we're looking at is, again, number of outliers. So you see how this is flattened, where the frequencies that would occur in the outer regions of this distribution are relatively similar to the frequencies that occur in the center of the distribution, kind of showing that we have few to no outliers. And we'll have an example of this in the activity this week, so you can kind of get an idea of what that shape would look like. So when it comes to calculating these, you do need to know these calculations for the exam, and they're reiterated on the activity, so that should be helpful. You actually get to work with them. But when we calculate skewness and kurtosis, again, we want to measure, right, how similar is a sample's shape to a population shape, the whole idea of statistical inference. So we use a z-score of skewness and a z-score of kurtosis to evaluate just that. All right, we want to know how close is a sample's distribution to a population distribution, and is it similar enough to a normally distributed shape that we can say the sample is normally distributed, right, relative to the population. So this top portion, right, is going to be the skewness of our sample, and Excel and SPSS do this for you, okay? The bottom portion is our standard error of skewness and kurtosis. We'll talk about this a little bit more, I think, in a couple of weeks, what standard error actually is. But this allows us to create two more standard scores, right? So far our standard scores are percentiles, z-scores, coefficient of variation, and now we're adding z-score of skewness and z-score of kurtosis. Right? So you have 5 standard scores that we've talked about in class so far, right? But this allows us, again, to evaluate our sample compared to our population, okay? Some notes about this. You can see the sample size n is in the denominator, okay? So having a larger denominator means you have less room for error in the numerator. And before we hang up the call, I'll show you why that is. Okay. We use a sample standard deviation to calculate the z-scores in the numerator. So again, that's why we identify these as sample skewness and sample kurtosis. Okay. And our results, when we end up getting our z-score of skewness and kurtosis, we need it to be within plus or minus 2 standard deviations from the mean, okay? Because we would be indicating if our skewness and kurtosis landed in, you know, greater than +2 or less than -2, though those outlier regions, if I go back to this empirical rule again, right? Very, very little data should actually exist in these regions, right? If we add past 2 standard deviations, it's a little over 2%, right? And the same thing goes for -2 or past -2 deviations. So when we look at our sample, right, we want our skewness values to land somewhere in this region in relation to the population distribution shape. Okay. So really quickly, I just wanted to, before we take off, I wanted to show why the sample size is so important, because I feel like that's a big topic that comes up where it's like, oh, we should use like bigger sample size. And this is why, because it helps us get a more accurate shape such that our sample, it's a little bit easier for it to be normal. Okay. So what we do, let's say this is a sample mean. So just to be clear, we have a sample here, and this is the mean of our sample. So X bar is what we use for the mean of a sample, right? In a given distribution, we are hoping that the shape arises from certain frequencies that are happening in the distribution, right? So a large number of frequencies happen in the center, smaller amounts of frequencies happen out here, right? And the more people we collect from our sample, right, all of these dots represent different people. The more people we collect from our sample, the more representative or the larger our subset of our population is. Versus if we get, you know, a sample and we say like, I want to pick 5 people. Well, we could probably assume, right, somebody in that of those 5 people might land here. One of those 5 people might land here. One might land here. But maybe you get some strange extreme score person who lands out here or who lands close to that person, right? Now your shape is no longer representative of your population, right? Because you have these random people who are existing in an outer region. So the more people we have, the more representative our sample is of a given population. And the same goes when we're comparing samples to populations, right? The way that we find out what a population mean is we just take a whole bunch of sample means and we stick them into a population. There's better. But, right, we could change this to say instead of a sample, we have a population, right? And this is no longer X bar, but rather mu. And all of these different dots represent sample means that have been collected over a large number of subsets that we've gathered. Child, just get down. Thank you. Okay. So when we look at skewness or kurtosis, right, if we're looking at skewness and kurtosis values within our population, right, if this is plus 2 and minus 2 standard deviations from the mean, if our sample is so skewed that it lands in this region or that it lands in this region, we can say that sample, that shape of that sample, is not representative of the population because it doesn't land where the majority should be. Okay, I'm hoping that makes sense. Usually this is a concept that really just does not stick with people. And we're gonna keep pounding this and pounding it because it's a very, I don't know, it's very complicated, I guess, in the wording that we can use, but that's all I have for you guys today. Does anyone have any questions before we go? All good? All right, well, enjoy the rest of your Labor Day. Eat some good food. I'm gonna go eat dinner now. So you guys have a good rest of your day, good rest of your week, and then if you have any questions, please feel free to email me, okay?
Thank you.
Yeah.
Bye.